My name is Gabriele Humbert. I am a postdoctoral researcher at the Urban Energy Systems Laboratory at Empa. Today, as Leah said, the presentation is about optimal design of synthetic methane production sites with direct air capture technology. Hopefully, we will see during the presentation what exactly all these terms mean. But first of all, some of the motivations. So we know that we have decarbonization goals. To achieve this, we need to increase the share of renewable energy sources, but it's also clear from the last decades that this is easier to be done in the power sector, while there are other sectors for which the use of renewable energy technologies, it's more challenging. These are typically defined as harder to abate sectors. Examples are renewable heat or renewable transport, for example. So for these harder to abate sectors, one of the ways to achieve full decarbonization or to increase, to reduce the amount of carbon is Power-to-X technologies. So in general, Power-to-X is a collective term for conversion technologies or conversion systems that turn electricity into carbon neutral synthetic fuels, such as hydrogen. This probably is the most famous currently, but also synthetic natural gas, liquid fuels, or chemicals. So Power-to-X is a effective way to have sector couplings between power sectors and other sectors which are maybe, as I said, harder to abate. Further, we have, as we know, with renewable energy sources and renewable energy sources generation, issues related to intermittencies of renewable energies and seasonalities. So we have a strong difference in generation between summer and winter. So in the slide here in the figure, you see the trends for PV production during the different months of the year in Switzerland. And it's clear that, as we also expect, production is higher in summer and lower in winter. And this means that in winter, for example, we need to import electricity from neighborhood countries. And in summer, we hopefully export excess of electricity to neighborhood countries if they want our electricity, actually. One way to face this intermittency and seasonality, again, is the use of storage solutions. So we already know that in current energy system and future energy systems, storage technologies will play a very important role. Here in the figure, you see a map of storage technologies as a function of duration of discharge. So for how long I can discharge the energy or store the energy, basically, and storage capacity, so how much energy I can store. At the top right of this figure, you see power-to-gas or power-to-X technologies as a way to convert electricity into fuels, mainly. And basically, this map is telling us that Power-to-X is a good way of storing large amount of energy for very long times. So it's a way to solve these long-term issues related to renewable energy sources. Additionally, Power-to-X can also be a good way to face some of the short-term issues. So here on the top right hand again, we have this mismatch in time between PV production in yellow and demand from EV, from vehicles. And in these scenarios or in these cases, Power-to-X can be used to produce fuels when there is an excess of electricity, and in the other way around, to use this fuel to cover unexpected increase of demand, or also to avoid peak. So to avoid basically congestion and do peak shaving. So the question now might be, yes, but are these Power-to-X or all these technologies be included or be considered in future energy systems in Switzerland? So from the studies that were conducted within Pathfinder, the answer is yes, actually, depending on the assumptions made or the scenarios considered. But regarding methane, hydrogen to methane, so production of synthetic methane from hydrogen, will be there with productions up to 5 terawatt hours or more than 5 terawatt hours. And also direct air capture, which is the technology I'm going to introduce later in the presentation, is also considered in some of the future scenarios. So basically, this is telling us that it's worth investigating these pathways. So at this point, just to provide a brief summary of the motivations for Power-to-X technologies. So the motivations are mainly four. They can provide long-term storage solutions. They can provide flexibility on the short term, so balance between supply and demand. They provide sector coupling, so how to connect the power sector with the sectors that are considered harder to abate sectors. And also, depending on the way these Power-to-X technologies are considered, they can utilize CO2, so they can do carbon capture and utilization, basically. However, as expected, there are challenges with Power-to-X systems. Here I listed some. Probably there are more. So in general, these are complex systems to design, build, and operate. Also, there are challenges during the storage periods, depending on the type of fuel that is considered, mainly for gas, probably because of energy density issues. There are high costs for production, transportation, distribution, and use. Then there is, at the moment, low technology readiness level, although this is growing fast. There is good interest in these types of systems. And so we see more and more projects providing good improvements in these TRL levels. And then they require significant power for the operation, of course, as expected. So here I also indicated in bold some of the challenges that we are going to look more in details in this presentation, or that at least we are trying to contribute to in the solution to the challenge, not to the challenge itself. The ones we are contributed to in our work. So the question now is probably why synthetic methane and all the different fuels that we can generate through these Power-to-X approaches. So synthetic methane has a relatively high energy density, although this can be probably discussed, and it can rely on existing infrastructures. This is key. So we know how to transport and how to use this synthetic methane. There is a lot of knowledge around already from natural gas mainly. The production of synthetic methane can utilize carbon dioxide, CO2, and the process is normally highly exothermic, which provides good potential for optimal thermal management or eventually waste heat recovery. There are different ways of producing synthetic methane. In this presentation and in Pathfinder, we focus mainly on the electrochemical pathway. This is because it relies on electricity that can be generated from renewable energy sources or excess of power. However, the issue at the moment, as you can see in the slide, is that the cost for this electrochemical pathway are too high. There I indicated the cost with DAC, which is direct air capture unit. The cost can be lower if we consider other types of carbon capture technology. However, costs are too high, and so we need to find ways to reduce this cost. The way we try to reduce the cost in this presentation in our work is by optimally designing the production sites. So the electrochemical pathway typically relies on the Sabatier reaction, which is the combination of carbon dioxide and hydrogen to generate synthetic methane. And as I said already, this is highly exothermic. So the key advantages, to summarize again, of this electrochemical pathway and Sabatier reaction is that we can utilize CO2, it can be powered by renewable energy sources, and that it is exothermic. So at the bottom there in the figure, you see the simplified schematic of how this can work. On the left-hand side, you have renewable energy sources or the grid. So they provide electricity, which is fed into an electrolyzer, which is a component doing the splitting of water into hydrogen and oxygen. So it provides hydrogen, which is fed into the methanator, which is also fed by the DAC, which is direct air capture technology, which is the technology responsible of producing the CO2. And then this methanator, as I said, produces synthetic methane, which is then stored into a big tank. So as I said, the key components, one of the key components is electrolyzers. There will be, or there has been actually already, presentations more dedicated to PEM electrolyzer or ways to produce hydrogen. But here, just to summarize, that PEM electrolyzers are very suitable here because they have high responsivity, which is very good when you couple these technologies with renewable energy sources that, as I said, are very intermittent, so they can have sharp variations in time, and they produce hydrogen at high quality. Here, one thing that is important to mention also is that the conversion efficiency of these units depends on the workload. And the point of maximum efficiency is actually at partial workloads. So what we find also within the Pathfinder project is that considering these curves during the design phase and of course operation phase as well, it's key in order to optimize design and operation of hydrogen systems. Now the other ingredient for the Sabatier reaction, as I said, is the CO2. So there are different ways of capturing CO2. Here you have a nice map with also TRL level. The map is actually from 2018, but especially as far as it concerns for DAC, the TRL level is still the same. So CO2 can be removed from point source emissions or directly from the air, so direct air capture. The key advantages of direct air capture technologies are in its scalability. So normally it's a modular technology, so more modules we add and more CO2 we can capture. And one very important advantage is that it doesn't have any geographical constraints. So we can locate these DAC units wherever we want, as far as it makes sense economically, obviously. So looking now at the physical principle of direct air capture technologies. So here we talk about solid sorbent, DAC, that they require both heat and electrical power to be operated. The physical principle is that we have a porous medium, which is a sorbent material, over which we have air from the environment, which is circulated, which is phase one of the figure here. And this is the sorption of the CO2 into the solid material. So the CO2 is captured basically from the air and absorbed by this solid material. Then in phase two, which is the desorption phase, we heat up the solid material with temperatures up to 100 degrees C. And this triggers a reaction for which the CO2 is taken from the porous medium and then can be circulated into a separated tank, which is the one storing the concentrated CO2 that then can be utilized for other purposes. So still concerning direct air capture units, the energy requirements of this unit vary significantly with ambient conditions. So here you have maps for energy requirements. On the left-hand side is electricity energy demand, kilowatt hours per tons of CO2 captured. On the right-hand side, you have the thermal energy demand. So what we can see here is that there are variations for the electricity up to 10 times, depending on weather conditions, and for the heat up to 3 times, depending on weather conditions. This tells us that weather conditions, when we size and operate, when we design and operate these systems, has a key, has an important role. And also that the selection of the location is also very important in order to minimize or reduce operational cost from these types of units. Now more specifically into the optimal design of synthetic methane production sites. So here we have a more detailed schematic of how the system looks like for these types of production sites. So again, on the left-hand side, we have electricity generation from renewable energy, so PV or from the grid. The PV is also connected to a battery. And this electricity used to feed electrolyzer, DSC, or heat pump, which is used to elevate the temperature from a district heating network or the temperature recover from an electrolyzer to then feed the DAC unit, which is our heat demand basically in this system. So the DAC and the electrolyzer also are feeding the methanator, and we have in this schematic, in this layout, also the possibility to recover the heat from the methanator, which can be then fed back to the DAC unit. The produced synthetic methane is then stored in a physical tank. So the way we tackle this optimal design problem is that we, first of all, select a production goal. So, for example, in this presentation, we consider 100 kilograms per day production of synthetic methane. So we want our system every day of the year to achieve this goal of 100 kilograms a day of produced synthetic methane. And also we have boundary conditions which are related to the specific location of the site. So we have weather data, we have a cost for electricity and also revenues from electricity. Then we have costs related to heat and revenues related to heat. Because here we assume the system to be connected to a district heating network, as I said. So more specifically to the boundary conditions, so we consider a 1 year horizon with 1 hour resolution and the city of Zurich. Here you can see the time series that were considered, but this is to say that the tool that we use is able to consider very strong fluctuations in boundary conditions, which are key in modern energy systems that are relying heavily on renewable energy sources, because it's important to capture this dynamic behavior and not to rely on approximated trends, which might end up in having suboptimal design or suboptimal operation, of course. So the approach that we used, I'll try to be quick here. It's a MILP approach, so mixed integer linear programming. So as I said, on the left-hand side, we start from the input data, which are the ones we showed in the slide before, plus techno-economic parameters, which are basically, for example, efficiencies, unit prices for each technology, lifetime of components, and so on. And for this, within the Pathfinder project, we also develop a techno-economic parameters database, which you can access from the QR code in the slide. So these input data are used to feed a MILP run. It's important here to say that in the MILP run, we have variables which are related to sizing and variables related to operation of the system. So we concurrently, within the same optimization problem, derive optimal sizes of components and optimal operation of the energy streams between components, basically. And then the outputs of this design approach are, of course, the optimal sizing and operation, and also evaluation of what we call value-adjusted levelized cost of methane, which differ from levelized cost of methane because we also consider revenues which may be derived from, for example, exporting electricity back to the grid. So here you have same system as before, but where I also highlighted which sizing decision variable and operation decision variables we have in our optimization problem. So you have in red sizing decision variables and in green operational decision variables. And as I said, the optimizer is able to return the optimal value for each of these decision variables. What do we optimize for? So typically we have two optimization problems, which are cost and emissions. But in this case, the results refer to cost minimization. So basically the question is for selected location, techno-economic parameters and desired methane production rate or production goals, what are the sizing and operational variables to achieve minimal cost? For minimal cost, we mean the sum of annualized investment cost, operational cost, and maintenance cost, again, annualized. So this is to say that when we minimize cost, we consider the whole lifetime of the system. And we minimize, as I said, both for investment and also operation. So how much energy the system consumes to achieve the desired methane production rate. So now moving into the results. So we have results in terms of optimal sizing, and here the important things to say are that the main drivers for the capex, for the investment cost, are the PV, the PEM electrolyzer, so the way we produce the hydrogen, and the direct air capture unit, which represent almost 90% of the total investment cost. Nonetheless, the high investment cost related to PV is also due to the fact that PV is highly beneficial in reducing operational cost. And the solution is highly sensitive to the maximum amount of PV space which is allowed in the optimization. So here you see in the table at the bottom, the selected PV field was always the maximum one that was allowed in the optimization. So this tells us that it's very important also in terms of reduction of levelized cost of methane to allow for or to identify sites that allow for very large PV installation, or basically for very large renewable energy sources availability. Then also in terms of waste heat recovery, or let's say optimal thermal management of the system, we found that this is very beneficial. It reduces the levelized cost of methane almost up to 6%, and reduces significantly how much we rely on district heating network. So we don't have to buy much. We don't have to buy much heat from the district heating network. Also, an interesting thing here is that when optimal thermal management is considered, the optimal size of the hydrogen tanks is also affected. It's increased to provide more flexibility to the system and to allow for a better utilization of the heat. In terms of optimal operation, we found that this is the very what drives the cost the most. So up to 72% of the total cost are related to operational cost. And these are mainly due to electricity. So the cost for heat imports are almost null or negligible, while the electricity cost mainly related to the PEM electrolyzer are very high. As we see also from a typical week that was selected in the figure, the bottom of the slide. This is because the electrolyzer had to be operated in order to achieve the methane production goal for most of the hours during the day, and it was turned on also during night, so leading to large imports of electricity. And a relatively high cost of electricity was considered in this problem here, in this design case, because the cost of electricity was derived from 2022. So it was an expensive year in terms of electricity. And so this, as I said, led to very high cost for operation. So the system considered, in order to reduce further down the cost of the methane production, has to focus on how to reduce this operational cost. We also looked at the impact of storage options within the design, within the methane production site. So we ran different cases, and one was without storage options available, and one with all storage options available, and then the optimizer could select the optimal storage options. So interestingly, batteries were never selected because of the high investment cost associated to batteries. But thermal energy storage and hydrogen buffers were always selected. And also an interesting aspect is that considering storage options in the design phase also impacts the optimal sizing of conversion technologies. So here we found out that when storage options are allowed, we have an increase in the size of the PEM electrolyzers, almost 20% increase, meaning that these two sizing steps of conversion technologies and storage technologies cannot be done as separate steps in the design process, but has to be done concurrently to account for this mutual influence between conversion and storage technologies. Other aspects we look at is into the impact of modeling level of fidelity of the DAC. So as I said before, the DAC units are affected by the weather conditions. So we look at what would results be if we disregard this influence of weather conditions. And we actually found that there is important impact in terms of estimated levelized cost of methane. So more than 3% difference if we used high fidelity models, so the maps I showed you before, or low fidelity models where we actually only consider average energy requirements from the unit. So now this is just to show some of the further research directions that we have within Pathfinder. So the results I showed you before were so-called deterministic optimization approaches, where we optimize system based on fixed boundary conditions, and the optimization is the specific one for those boundary conditions. But then when the system is built, maybe the boundary conditions it was built for are not the real one. So we want to account for this uncertainty already during design process. The way we do that in this example here briefly is by considering Monte Carlo optimization. So we run a large amount of deterministic optimization of the optimization I showed you before. And then we look at a large amount of solutions, and we try to average these solutions in a way that we can generate robust solutions. So the good news here actually for this design case is that we did that and we didn't find too much difference compared to the deterministic approach. The sensitive variable, let's say, for this problem is the hydrogen tank, meaning that for all the scenarios that we built and for all the scenarios that we consider, the variable that was changing the most between the different scenarios was the size of the hydrogen tanks. But overall, the most, say the sizes that occurred the most, even in these Monte Carlo simulations, was very similar to the ones that was selected in the deterministic approach. Now, to conclude, still related to synthetic methane production sites, we have projects here at Empa. So currently we have a demonstrator for mobility of the future, which is called MOVE. MOVE at the moment hosts a 180 kilowatt electrolyzer and can store hydrogen at high pressures, on 900 bars. However, now we are in the process of expanding this demonstrator and adding also the possibility of producing synthetic methane with the same design or pathway that I showed in this presentation. So with a direct air capture unit, which is from Climeworks, and also an innovative methanator concept, actually. So of course, the goal is to provide real-world scale demonstrators to collect data and also to test control strategies. So for this, there are already publications available, which I listed at the bottom of the slide. So yeah, to conclude, the key takeaways is that optimal solutions for energy systems in general are highly sensitive to input parameters. And this needs to be selected carefully, or the uncertainty needs to be taken into account. Then the operational costs are the dominating factor for these synthetic methane production sites with direct air capture technologies. The use of storage options impact optimal sizing of conversion technologies, and that optimal thermal management reduces the levelized cost of methane quite significantly. So it's always important to consider the possibility of optimal thermal management already during the design stage. A bit in terms of reflections and future research directions. So regarding design of energy systems, for sure, we would like to explore more how to include uncertainties already during the design phase and how to create robust optimal design. And for the same reasons of creating robust optimal design, we also want to include more and more operational constraints in the design problems and to reduce the gap between what is done at design phase or let's say predicted at design phase and what is obtained at the operational stages. Then in terms of synthetic methanes and also direct air capture technologies, I would say the main point there is to have infield data, to have validations of our models and our assumptions, and in general to find ways to reduce cost, both in terms of investment and operation. So yeah, that's it from my side. Thank you very much.